Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the conference. Artificial brains, a swarm of mathematical programming algorithms. Applications in image processing. During the Second International Conference on Advanced Sciences, Astrodynamics and Remote Sensing organized by the Faculty of Mining, Geology and Civil Engineering of the National University of San Cristobal de Huamanga, Peru. Conference prepared and edited by Jesus Velasquez Bermudez. His resume may be found on LinkedIn. There are two approaches to process data from a super measurement system that provides a non-enumerating amount of data, in real time and asynchronously: parallel analytics and distributed analytics. These two terms seem to be the same, but they are different and complementary terms. The parallelism and distribution of computing processing goes beyond the simple construction of parallel mathematical algorithms. It implies a way of facing problems with the bottom-up approach, from the description of atoms to integrating the vision of the entire system. It is a way of thinking about mathematics, according to the development of computer technologies. This is consistent with the abolition of monolithic computer applications, to make way for distributed applications based on microservices. Then the next step of advanced analytics is sparse analytics, which is based on parallel and distributed analytics. Asynchronous parallel analytics, called asynchronous parallel optimization by Velasquez, in 1995, 1997, and 1998, is defined as the act of solving a mathematical problem, using multiple cores on a computer, or on a computer grid, using modern multiprocessing environments, uniting the theories of decomposition and partition of large systems, that allow to structure complex multi-level mathematical models. Parallel analytics distributes workloads for data analysis, across multiple nodes in a server cluster, rather than addressing a large problem on a single supernode. The algorithms run on each node, processing a subset of the data. When processing is complete, or whenever required, datasets are aggregated, or rejoined, to generate collective information. There are many advantages of the asynchronous parallel approach. Less time to get information. By putting multiple nodes to work on the same problem, you can get insights from the data much more quickly than would be possible by running an analytics application on a single supernode with linear processing. This is a huge benefit when you want to get quick responses from massive amounts of data, and asynchronous processing allows to produce information that can be stored in memory until it is required by some subproblem. This speeds up the solution. In addition, it requires less demand for resources, avoiding congestion in computer systems. Distributed analytics is based on parallel analytics, and it is the distribution of the mathematical modeling process in many agents that act simultaneous and independently when they received information from its exogenous environment. The process can be summarized in the following steps. From a top-down process analysis, it is possible to construct mathematical or logical rules of interaction between multiple agents, representing each one a part of the system. Jointly, all the agents can represent the state of the reality. Starting from math, or logic rules, following an approach bottom-up, it is possible to build segmented, or atomized, models of the real world. Using asynchronous parallel processing, it is possible to define the simultaneous actions of all agents that keep on the right path a cyber-physical system. This processing is different from the traditional one, based on the synchronized use of mathematical models that are executed periodically. Autonomous real-time distributed optimization. Mathematically, this process may be supported by large-scale optimization algorithms, aimed at solving very large optimization mathematical problems, based on the intensive use of methodologies for partitioning and decomposition of systems. New technologies and big data shift from traditional optimization based on synchronized moments, to modern optimization, based on real-time events, in which models will run autonomously, when necessary, by events. Autonomous real-time distributed analytics is a topic open to researchers in advanced analytics. Human knowledge is supported by two types of models. Mental model, it is the abstraction or conception of what is perceived by individuals about a given issue or problem. Mental models are constructed with the knowledge, experiences, assumptions, perceptions, intuitions, informal inductions, deductions, and values of the individual. They are elementary models that are not exposed in public and therefore have a validity limited to the individual. They have their origin in the evolution of the human being, hominization, from the most primitive ancestors, Australopithecus, to the appearance of our species as we know it today, Homo sapiens. All human beings manage mental models, very quick to solve, and, in their absence, easily copy themselves from a more influential individual, and more recently, are implanted in human beings through the ochlocracy of mental models distributed by social networks. When intelligence works under this model, we will call it mental intelligence. Second, mathematical model is a scientific representation which make use of mathematical language to describe or to explain the portion of reality that is of particular interest to an individual. It is the result of the research carried out by certain humans. The mathematical models are growing as analytical tools that provide greater processing speed to the investigation. For its understanding requires formal training in mathematics and in the science being modeled. These models increase the intelligence of human beings, creating large differences, chasms, between them. When intelligence works under this model, we will call it mathematical intelligence. To evolve from mental intelligence to mathematical intelligence, the human being requires another type of intelligence that allows to perform the analyses to understand and discover the models that govern the universe. We will call this intelligence analytical creative intelligence. This intelligence can be considered as the highest level of human intelligence, since it is what allows to grow in the discovery of mathematical laws, and in general new knowledge, which is the engine of the scientific and technologic development of humanity. To create creative artificial intelligence, little progress has been made and therefore, it seems that is distant the time when artificial intelligences be capable of creating knowledge that can be used to develop creative cognitive robots as part of the eye. From human brain to artificial brain. The human brain is too complex to understand its functioning and synthesize it based on a unique mathematical algorithm. Neuroscience studies allow us to understand that within this high complexity there are infinitely large structures and infinite parallel processes that complies with many rules of regularity, hierarchy and symmetry. Then, based on these observable results, artificial approximations, aimed at building artificial brains for organizations can be constructed. In this understanding, large-scale optimization methodologies play a very important role. Now we can explore where we are. Traditional AI has concentrated on developing mathematical models, which try to imitate the functioning of mental intelligence, based on the structure of functioning of the brain, to represent the mental models associated with the processes of intuition, perception, deduction, just like humans, without using formal mathematical models, using fundamentally data-driven models. This process has been successful in relation to advanced predictive analytics since machines are able to emulate and overcome, in many facets, the mental functioning of humans. For example, pattern identification is increasingly performed by robots with greater precision and greater speed. This success is magnified when AI is given the ability to chain sequential recognition of multiple general patterns to a specific individual pattern, for example, identifying a specific person. And where are we going? Augmented artificial intelligence will be the new era of artificial intelligence will be based on the study of the operation of the neocortex and the real-time communication between algorithms, or cognitive robots, to build networks of mathematical models that allow organizations to act in a similar way to the human brain, making intensive use of distributed processing. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus and hippocampus. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. Connectivity is based on a sparse network, which can be assimilated to an array. The hypothalamus must coordinate all the processes that the human being carries out. The artificial hypothalamus must connect the multiple mathematical models, algorithms, that are part of the artificial brain, exchanging information between them to obtain a common goal, mathematically an objective function. This activity must be autonomous, permanent, and based on distributed processing. The hippocampus. Storage structures and processes from the decision-making that must be faced permanently. The artificial hippocampus is based on the mathematical synthesis of the information generated by algorithms and problem-solving processes, to use it in new runs of these algorithms to speed up the problem solution in real time. Artificial hippocampus store, like in the humans, the experience, and the knowledge acquired over time. The central axis of this possibility lies in developing a standardized language between algorithms, that allows to build an artificial hypothalamus so that multiple algorithms, representing agents, interact autonomously in real time, taking advantage of the information stored in an artificial hippocampus. This could be called Mathematical Programming 4.0. Based on distributed parallel mathematics, and not on the traditional concepts of monolithic and sequential electronic calculus. When formal mathematical models of real systems are known, the inability to use them, in human everyday life, is directly related to the very low speed of mathematical calculation that humans have, which does not allow the scientist to solve in real time the mathematical problem associated with the knowledge that he has. For robots, computer technology has overcome this inability, allowing them to solve in real time increasingly complex real problems. Only when humans will be able to bring the mathematical calculation power to the human brain, we can use the known mathematical models in human everyday life. However, organizations can already build their own artificial hypothalamus, using existing computational power. Jeff Hawkins is an advanced researcher in the application of neuroscience to the development of artificial intelligence. As a result of his studies at Numenta Incorporated, Hawkins proposes the sparse artificial intelligence model, whose main characteristics are. Hawkins proposes the sparse artificial intelligence model, composed of columns and layers that performs robust object learning and recognition. Columns integrate their changing inputs over time to learn complete models of observed objects. Lateral connections across columns allow the network to more rapidly infer objects, based on the partial knowledge of adjacent columns. Because columns integrate input over time and space, the network learns models of complex objects, that extend well beyond the receptive field of individual cells. The Hawkins network model introduces a new feature in cortical columns, that proposes that a representation of location calculated within the subgranular layers of each column. The representation of location is relative to the object being sensed. Pairing sensory features with locations is a requirement for modeling objects and therefore must occur somewhere in the neocortex. Hawkins proposes it occurs in every column in every region. The network model contains 2 layers and 1 or more columns. Simulations show that small single-column networks can learn to recognize hundreds of complex multidimensional objects. Given the ubiquity of columnar and laminar connectivity patterns, the columns and regions have more powerful recognition and modeling capabilities than previously assumed. In summary, the modeling of the structure of neocortical regions is organized into columns and layers. Connections between layers run mostly perpendicular to the surface, suggesting a columnar functional organization. Some layers have long-range lateral connections, suggesting interactions between columns. Similar patterns of connectivity exist in all regions, but their exact role remain a mystery. All regions have a motor output. Another important contribution of Hawkins is related to the multiple brain models of the same object working cooperatively. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. Structurally similar to that of the human cortex. In optimization models, it is common to use a matrix that relates columns with variables, and equations with rows. Depending on its complexity, the ways to divide a system may be non-numerable. The diagram shows a 2-level structure. This diagram shows a 3-level structure. This evolution may be summarized as the shift from artificial intelligence to augmented artificial intelligence, that evolves from artificial intelligence very powerful in pattern recognition, to intelligence that powers the human brain, becoming an exobrain with high decision-making capacity, in real time, and autonomously. The decision support systems, DSS, were conceptualized as a set of mathematical models that exchange information between them, working offline. The artificial brain is the evolution of DSS under the Industry 4.0 revolution, that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. So, the artificial hypothalamus, a part of the artificial brain, is the algorithm that controls the workflow of the models of the decision support system. It includes a general math language between algorithms that guarantees that the system is in the optimal path. This is based on the duality theory. In real-time and uncertain systems, the concept of an optimal point must be replaced by that of optimal path, as the one who is always close to the ideal optimal points. The algorithm that simulates the hypothalamus is assembled by Optex, the HI's artificial intelligence to generate mathematical programming solutions, using the models that traditionally make up a decision support system. Monolithic mathematical models. Modular mathematical models. At the beginning of the decade of the 60s of the last century, they presented the first works aimed at dividing and starting the monolithic models to convert them into modular models. In the opinion of the speaker, this effort is made to make mathematical models more manageable, which resulted in lower memory requirement, and faster solution of mathematical problems. Parallel computing. The evolution of computers, from the single-processor computer to the multiprocessor multi-core computer, opened the way to large-scale methodologies towards parallelism, since the mathematical bases were already implicit in all the works of Dantzig, Wolff, and Benders. Today, they become fundamental methodologies, since the computers that are most used are multi-CPU and multi-core. Additionally, connectivity between computers turns the limits of parallelism into an infinite number of possibilities. This gives the opportunity to the birth of artificial brains. All the developments, in mathematics applied to solving real-life problems, converge to parallel processing and the large-scale mathematical programming. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. Algorithms swarm. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots. But the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. Data reconciliation of satellite image using distributed Kalman filter, DKF. Rudolph, Rudy, Emil Kalman was a Hungarian-born American electrical engineer, mathematician, and inventor. Rudolf Kalman was born in Budapest in 1930. After emigrating to the United States in 1943, he earned his bachelor's degree in 1953 and his master's degree in 1954, both from the Massachusetts Institute of Technology. Kalman completed his doctorate in 1957 at Columbia University in New York City. Kalman was most noted for his co-invention and development of the Kalman filter, a mathematical algorithm that is widely used in signal processing, control systems, and guidance, navigation and control. For this work, U.S. President Barack Obama awarded Kalman the National Medal of Science on October 7, 2009. Today, Kalman filter and all its variations, it is the most robust hybrid predictive analytics method that exists. Under the state estimation approach, an uncertain dynamical system, whatever it may be, can be conceptualized as consisting of two systems or components. Physical model. The system dynamics can be represented based on a set of differential equations, or differences, based on mathematical laws. Typically, these equations are referred to as the system model. The state in which the system is located is referenced by the vector of state variables, xt. The state equation, which defines the gradient of state variables, has a known structural function that depends on a set of parameters, beta t. The ut vector is related to control variables, which humans can manipulate to control the system. Observation model. On the other hand, a measurement system, which observes the dynamical system by the variable zt, is related to the state variables by a vector function ht. The vector function ht can directly measure state variables, or measure transformations of these variables. Additionally, this observation system can include multiple measurement systems, from different sources. Together, the two components make up what in artificial intelligence is called a hybrid system, which combines information from the physical model with measurements from the observation system. To build it, two types of knowledge are usually required. That of the field expert, in this case an aerospace engineer, or similar, and that of a data scientist. The traditional is to use models based on mathematical models of the system, or models based on the data. The construction of the state equations requires complex mathematical knowledge, and therefore they are not commonly used. However, without an observing system, these isolated physical models contribute little to the online estimation and forecasting of the system's trajectory. Data-driven models are much easier to build, but they ignore scientific knowledge of the mathematical laws that govern the behavior of the system. By integrating the two models, state estimation becomes a robust hybrid method, capable of producing the best possible results, in terms of forecasting the state of the system. The concepts of state estimation are applicable to multiple types of systems. A few are mentioned below. Vehicles guidance, satellite imagery processing, hydroclimatic variables. State estimation models assume that we ignore the past almost as much as the future, and for the present we have a rough idea of where we are. As we acquire information, uncertainty in all directions must decrease. Processing satellite images via Kalman filter. The process begins with the acquisition of the images produced by the satellite. From the original variables, new images processed by a predictive analytics method, in this case the Kalman filter, must be acquired. Finally, the objective variables must be produced, those that are of interest to the end user. A satellite can produce multiple images, of different variables. In this case the filter model can be applied integrally to all variables, to make the relevant corrections, considering the correlation between errors, or noise, of the images. It is also possible to obtain multiple images from different satellites. The filtering process should also be applied. If the number of satellites, and the number of satellite images, grow, it is theoretical to think about solving the problem through of a monolithic model. The indicated thing will be to use a distributed advanced analytics for satellite image data reconciliation. This system could be thought of as a Kalman standard filter by image satellite, and a Kalman filter concentrator, or a fusion filter, for multiple image satellites. With this architecture, we have original images, and filtered images using data from the rest of satellites. Case: GNSS Satellites Network in Perth, Australia. This case has been extracted mainly from the paper Consensus-Based Distributed Filtering for GNSS. DKF has been applied to a network of receivers tracking Global Navigation Satellite Systems, GNSS. This is relevant as soon the proliferation of low-cost receivers will give rise to a significant increase in the number of GNSS users. Although each single receiver can run its own local filter, the precision of such single receiver solutions is generally much lower than its network-derived counterparts. With the increase in the number and types of GNSS receivers, many more GNSS users can establish their own measurement setup to determine parameters that suit their needs. With the DKF or other distributed filtering techniques, GNSS users can therefore achieve high-precision solutions without the need of relying on a centralized computing center. The way the nodes interact with each other to transfer information is referred to as the interaction topology between the nodes. The interaction topology is often described by a directed graph whose vertices and edges, respectively, represent the nodes and communication links. To present DKF, it's convenient to consider some notions about network representations, mathematical methods used to represent network structure and connectivity. Networks are mathematically represented by graphs where vertexes denote nodes of the network and edges of the graph are the existing communication links between nodes. Central Kalman filter, or consensus filter, formulation and classification of different available filters and their equations. Consensus problems are widely considered in computer science. They basically form the field of distributed computing. Formal study of these type of problems goes back to people who were working in management science and statistics in the 1960s. In a network of some dynamic systems, called agents, consensus means to get an agreement regarding some common interest of the agents which depends on the states of all of them. A consensus algorithm, or protocol, is the law which specifies the information flow between an agent and its neighbors to reach to the consensus in the whole network. Local Kalman filter, its equations and justification for their use in terms of adaptability and optimality has been presented previously. To illustrate such applicability, Kodabande et al. Simulate a network of 13 GNSS receivers located in Perth, Western Australia, each receiver having data links to its neighbors with interstation distances up to 4 kilometers. The figure represents a network of 20 nodes with their two-way static communications links. The nodes remain unchanged over time. Two networks are shown. Network with 49 links, and network with different numbers of links over 4 sessions, R, Y, G, B. 7 links in session R, 6 links in session Y, 8 links in session G and 7 links in session B. The number of links between the nodes can be different for different sessions. Each session represents a graph that may not be connected. In a connected graph, every node is linked to all other nodes at least through one path. This peer-to-peer distributed estimation method gives DKF's algorithms with many different consensus strategies on estimates. DKF modifies the local processing scheme for each sensor to have the product representation hold at each instant of time. Then, when the fusion center receives the parameters from all sensors, the convex combination can be applied to compute the optimal global estimate. This can be of great benefit if communication channels with unreliable links must be considered, since the full information on the target state is distributed in the sensor network. However, for completeness, it should also be noted that the modified local parameters are not optimal anymore in a local sense. One could say that local optimality is given up for the sake of global optimality. The network receivers I equals 1, 2, 13, are assumed to track GPS satellites over 16 hours from 8 o'clock to 2400 hours Perth local time, on February 6, 2016. The observation sampling rate is set to delta equals 1 minute. Thus, the number of observational periods, time instances, is 960. The data sending rate delta in the experiments is delta equals 5, 10 and 15 seconds. Thus, the number of iterative communications between the neighboring receivers takes the values not equals 4, 6 and 12. The consensus protocol 3 is applied to the CKF of each receiver. As the satellites, with code PRNXX, revolve around the Earth, not all of which are simultaneously visible to the small-scale Perth network. Their visibility over time is shown in left panel of the figure, in which the satellites with elevation angles smaller than 10 degrees are excluded. There are 31 GPS satellites with PRN4 absent. PRN22 has the maximum duration of visibility, while PRN21 has the minimum duration of visibility. Note also that PRNs 2, 6, 16, 17, 19, 26 and 32 disappear, set, and reappear, re-rise. That is why their visibility is shown via two separate time intervals. The right panel shows the trajectories of the ionospheric pierce points on the ionospheric single layer that are made by receiver to satellite line-of-sight paths. Some results. Before discussing the precision performance of the CKF solutions, the network-based Central Tech solution is compared with the solutions that are obtained by the data of one single receiver only, referred to as the local tech. At the filter initialization, the standard deviations of the local tech solutions is 13.5, approximately 3.6 times larger than those of the central tech solutions, indeed, square root of the number of nodes. This is because each of the 13 network receivers independently provides equally precise solutions. In that case, the central solution follows then by averaging all the 13 local solutions. Due to the common dynamic model, the local solutions become correlated over time. Two different worlds. Without fear of being wrong, it can be said that as people and organizations travel the path from arithmetic to parallel thinking, an abyss is being generated, which is concretized in the speed with which a society produces knowledge and wealth. The new way of mathematics is directly related to the parallel thinking, and today it can be said that, like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Not teaching young professionals the principles of parallel rationing, derived from the new mathematics, is a serious mistake. Each society that does so will end up paying its consequences, which in simple words, will lead to poverty, and a growing scientific backwardness, an abyss, which generates two different worlds that will not be compatible. Finally, there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.